So let's take a look at the other Rust project to show you some more things. A heap overflow. We've done a buffer overflow, but we didn't do a heap overflow. So here's what that looks like. If you, in C, let me get my code. All right. The heap is for temporary storage of variables, so you have to allocate space on the heap, and that's what malloc does. So I allocate 20 bytes of space on the heap and call this name1, and allocate another 20 bits and call that name2, and then just like before, I read them in from the user and print them out. So let's run this one. There's the compiling statement. And then run it. All right. So we put in a name which is 20 characters long, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. And put in another one that's 20 characters long, like B's, I guess. And I allocated 20 bytes. I guess, all right, there we go. And now, name address 2, so it looks like it worked, printing out the expected values of names. All right. Now, if I run it again, and I use 40 character long strings, I'll just copy and paste them. There's 40 A's and there's 40 B's. And now, name1 is a whole bunch of A's and then a bunch of B's and then extra junk here. Name2 is B's, but then it has the string name2. Both of them have overridden their range on the heap, leaking into the next heap chunk, adding a bunch of weird junk to them. So this is, how is the developer supposed to understand what will happen here? Crazy things happen. The data from one leaks into the other. They gain extra data at the end that was supposed to be metadata, like the name of the item and such. This is incredibly cool. And of course, that kind of garbage will not happen to you in Rust. So here's the heap. Now, one thing that's great about Rust, a variable I didn't show you here, is dangling pointers and double free. Let me just mention that. Notice we did not ever free these items. So if this was a real program, when you allocate something with malloc, you're supposed to use it. When you're done with it, you're supposed to free it. And if you don't, then people can refer to it later when you think you're done with it. So failing to free something or freeing it twice both lead to serious security problems in C. In Rust, this cannot happen because you allocate space on the heap here with this box thing, and there is no free command. What happens is it's got a scope. The scope starts at the curly brace, defining the block of code where you defined it, and it ends at the closing curly brace, so the object will only exist in that scope. And as soon as you leave the scope, it'll automatically be freed just once. You can't free it twice. You can't forget to free it. This is, again, one of these brilliant things that is so much better than C, which places this painful burden on the developer in a complicated code base of where did I define that thing? Did it really get freed? Am I sure that free function didn't get called twice? And so on. It's too easy to make that mistake, and you just can't make that mistake in Rust. It's just designed to avoid doing that to you. So we can compile it again with debugging information and do our heap. And so right now they start out containing nothing. I just put, I guess, a period at the end of the sentence so we can see it. Now if we put in 20 characters, it'll work fine. 40 characters is the interesting acid test. So we put in 40 and put in another 40. Then they end up, name1 contains 40 and name2 contains 40. Just like they should, even though I defined them new. See, I didn't specify the length up here. You don't need to specify the length. It will automatically grow to whatever side is needed. So just like the other ones, and you can use GDB to examine where they're stored, but it's the same way it was with the stack that we did before. All right, and I did make one with a dangling pointer where you define something and then you free it, and then you try to print it out after it's been freed. So let's try this one. This is dang-p. One of the many things that can go wrong when the alloc and free commands are not used correctly. Here's the simplest case where you define it with malloc to be name1, then you free it, but then you use it after free. Use after free vulnerability. So if you compile that thing and run it, Okay, and now I put in A and B. Then name 1 changes into identical to name 2 with the same value. So this is another bit of complete madness to drive you nuts. These variables are now identical, pointing to the same storage in memory, and how you were supposed to know that would happen or cope with it is, again, just a mind-boggling thing no one can understand, and therefore you get security problems. And of course, that won't happen in Rust. There is no free command. You cannot accidentally free it and then use it. Down here, I'm going to make this mistake. I'm going to define on the heap, using the box command, a mutable variable, name1. Then I'm just going to go out of scope, so name1 will be freed. Then I'm going to try and print the contents of name1. So let's try this one. And this. And then compile it. And I can't even compile it. The compiler will notice you try to reference name1, but it's fallen out of scope and doesn't exist anymore, so you can't possibly make this use after free mistake. You won't even get to compile your code, which is great, of course, much better for the developer. There's no chance of you making code that's this mistake in it and sending it off to be distributed to people and used and cause problems. And then there's one here with a memory leak, which is another problem where you just keep allocating more and more space over and over. You call this thing 1,000 times, it keeps allocating more and more and more memory. And anyway, so I got a few other examples of flaws here. Here's the memory leak in Rust. And I don't remember what the point of this one is. I don't think Rust can catch you. I think the point is Rust cannot stop the memory leak. You'll see the memory usage. That's like the command injection. I don't think Rust can stop that. And there's other ones with duplicate pointers and such, but I don't think I'll go through them in detail here. You get the idea. These are some of the flaws in C and why people love Rust. It doesn't mean you can't have security problems, but it ends a whole category of particularly mind-boggling problems that have been driving us all nuts in C since 1979 when it started. All right, I'm going to stop recording this.